All right, welcome back. And today we are going to do a question called permutations. Now, this question is also one of the very common question, but using a very common technique. And this technique, actually, I'll try to let you think of what technique you have to use. So let's look at the problem. Permutations. Given a collection of distinct integers, return all possible permutations. For example, if you get 1, 2, 3, then you get all of these permutations over there. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1. Now, whenever you have questions about like permutations, or at least like if your output, especially if your output is all the arrays, instead of saying like how many permutations there are, you actually return the arrays, the different arrays. It means this question is usually not about time efficiency. The reason is because no matter what, you're gonna have to output all of the permutations. And how many permutations are there? If you've taken combinatorics, you'd know that how many permutations when there's 3 distinct numbers, it's 3 times 2 times 1, which is, so imagine if you have n numbers, the time complexity will be at least n to the, like the exclamation part, like n power. I forgot what it's called, n factorial. All right, so now how are we gonna do this? So the thing here, the technique that we have to use is actually called backtracking. And backtracking, I don't know why they gave it such a fancy name, because for me, it's basically just recursion and just like correcting your mistakes. Well, I guess that's called backtracking. But yeah, so whenever you have a question like that, always think about using backtracking. And how do you do backtracking? You use recursion. Now let's look at the iPad and let's use this example and then play with it. So yeah, so let's take this example, 1, 2, 3. And then you know already what the output is look like, but basically I want to use this example to demonstrate what backtracking is. Backtracking, think of it as a brute force game, or a brute force way to try to solve a game. In this game, you're actually not trying to solve anything, but you're trying to solve all the possible moves that there are. That's what permutations are. So, what are the moves? Imagine if intuitively you would do this in your head, not even code-wise. What would you do? You would first say, okay, the first one, for the first permutations, I want to keep the ones here and then just permutate here. So that means 1, 2, 3, and then swap 1, 3, 2. And then, okay, what about now? We have 1 instead. We have 2 instead, and then 3. So then you do the same thing, and then you get all your permutations. But essentially what you're actually doing, if you try to use that intuition and turn it into something that's more systematic, then what you're essentially doing is you are making a decision tree. So for example, if this is your initial set, in the end, you're gonna have all of your set of permutations here. But first, what do? So you make decisions. Here, you want to swap 1 with 1. So for example, here you choose to be first, have 1, etc. Here would be 2, etc. And then here would be 3, etc. Right? And then how many ways can you do this guy? And then you keep exploring. 1, 2, 3, because there's only 2 options, and then 1, 3, 2, 2, 1, 3, 2, 3, 1, and then 3, 1, 2, 3, 2, 1. Basically, that's what you're doing with backtracking. And essentially, what you're doing backtracking is first, you haven't done anything yet. And then later on, you go into this state, and then you realize that's the end state, and then you record that. And then you backtrack, you go back. That means you kind of redo this, and then you go back here, and then you go into this state. So let's make it even more systematic. Okay, now we understand a little bit more intuition of what we have to do. So what do you actually do? What does these arrows actually mean? Every time you go into a state, what does that actually mean? All right, so here, because we just want to go into all the permutations of these numbers, what you can do is you can swap numbers. Like for example, for here, we care about first index. And then we care about second index, and then third. So what does that mean? So here, for the first index, I want to swap it with the index 0, for example. Let's see, index 0, right? Actually, let me redo this. I'm gonna change it to 0 so that it makes more sense because we are computer scientists. Okay, imagine we care about this. And then for the 0th index, we can either do 3 ways, right? We can go either we change it to the 0 index, swap with the 0 index. So that means the first you're gonna have 1, right? You're gonna be swapping with 1, and then you have 2, 3, and then this one you decide to swap the first index with the first index. So 0, which is 1, you're gonna swap with 2. So you're gonna swap these guys. So you're gonna get 2, 1, 3, and then here you're gonna get 3, 2, 1. Right? Because essentially we care about the 0th index here, right? And then we have 3 cases. Either you swap with yourself, which is this one, or you swap with this guy, which is this one, or you swap with this guy, which is this one, right? And then what you want to do is here you continue deeply, you recurse on it, right? So you call the same algorithm, and then what it's going to do is here it's actually just looking at these guys, right? So we do the same thing, but instead we start at the first index now. So the first index, I could swap it with myself, 0th index. So that would mean 2 swaps with 2, so then that's 2, 3. And then I could also swap with the second index, which is 1, 3, 2, right? Because now that you're over to the next step, these ones are fixed. These ones are fixed, so you're not touching these anymore, right? So everything here, actually I'm gonna draw it out more. Everything here, and then here it only has 1, 2, 3. Here 1, 3, 2. Right. So let me show you what's fixed. So in here, you care about this guy, right? And then here you keep swapping. And then here, in this level, you're only swapping this index. And then at the end, you're swapping the last index. But the last index you can only swap with yourself because you have no one else to swap. So that's basically how you go into backtracking. You go through all of these states, and then once you get to the end, you do not have any index to swap anymore, and then that's how you record all of your that's how you record all of these cases. Same thing here, 2, 1, 3, and then etc, etc. All right, so I'm gonna explain it kind of one more time to make it a little bit more clear. And it's not exactly how we're gonna implement it, because this way is actually not efficient because we have to create more arrays for this. But I'm gonna show you using a empty array first, and then you choose to put in certain values. So backtracking basically is like this. Okay, and think of a game. Imagine you have a puzzle, and then you go to different states, and then once you're done with the end state, you go back. So here it's like, okay, I decide to put 1 in my empty array. So these are numbers I can't put. I can only put them once. So I want to put 1 in here. So I have this, right? And then once I have 1, I could either put 2 or 3. Let's say I decide to put 2 in here. These are arrows. Now I have 1, 2, okay? So I decide to put 3, 1, 2, 3, okay? And now I have an end state, so now my solution, I'm gonna add this state to it. So 1, 2, 3, okay? And now I backtrack. So backtracking gets me over here, and then I can go back and try another value, but there's no more value because I can only do 3. So that doesn't work. So I'm gonna backtrack again. I'm gonna go all the way to this state, and I'm gonna try the other value that I haven't tried, which is 3. So that I will get 1 and 3, right? And then after 1 and 3, I only have one choice, 2, 1, 3, 2, right? So every time I have an arrow and a number, that's appending. Okay, and now that I'm in the end state, I'm gonna add another one of this end state, and then I'm gonna backtrack, and then can I go anywhere? No, that is the only value I can go. All right, backtrack again. Have I tried all the values? Yes, I have. I'm gonna backtrack again, so now I'm here. So as you can see, I was here, and then I backtracked to here, and then back to here, right? Because I've exhausted all the possibilities. What are the other possibilities? 2. So now I have an array 2. And then what can I try? I could try putting 1 here, which is 2, 1. And then later on, I could only put 2, 1, 3, because that's the only possibility, right? And then I backtrack and I go back here, and then I could put 3 here, 2, 3. And then there's only one possibility, which is adding a 1. So 2, 3, 1. All right, so you get the gist. I'm just gonna draw this one out real quick. So I got 3, and then I could do 2. So 3, 2, and then here's 3, 2, 1. Actually, wait, let's do 1 instead. 1, 3, 1, 2, 3, 1, 2, 2, 3, 2, 1, 3, 2, 1. All right. So then every time we went to the end state, that's basically our solution. So, you know, this one was supposed to go here, 2, 1, 3. This one's here, this one goes here. So then that would be your solution space. So yeah, so I hope this is the best explanation of backtracking I could do, is you go all the way to the end, and then once you go back, you kind of fix it. You kind of fix what you did, and then you continue to try to explore different possibilities. That's pretty much backtracking. All right, cool. So how does this translate to code? So in code, kind of like what I said before with the swapping, instead of just adding these numbers, we're gonna have this array that's already here, and then we can play with the state, right? We could play with the state by saying, okay, first I wanna swap this guy, right? And then I'm gonna swap the second guy, and then the third guy. I'm gonna swap with wherever number. I think it's easier if I just show you the code. All right, so let's do the code. By the way, what's the time complexity? It's n factorial, and then also space complexity is n factorial, because there are just so many numbers here. All right, so let's do this. So here, I want to start with having a result array to make sure that that is the final array that we're going to be using. And then we're going to add a helper. The reason why we have a helper is because we are going to recurse on it. So we need a permute helper. So we need to use this function to recurse, because while remembering 2 things, start and end. Start and end, which means which are the numbers I actually care about. Because recursion, what's good at doing is imagine everything that imagine everything in front of you, you've already done. The function works. And then what would you do differently, right? So that's the basic of recursion. So first we have a base case, right? So if we only have one number, kind of like here, once we only have one number, like if we look back at the iPad, like these guys, you know, you only have one number left, right? There's no more areas to go. Once you only have one number, you're just gonna output. So it's gonna be, you're gonna attach it to the result. You're gonna attach whatever number you have. Nums, that's the array that you have that you're gonna be manipulating. And while you manipulate it, you're gonna backtrack. So you're gonna unmanipulate. I'll show you what that means later. So yeah, so we're gonna copy it. The reason why we copy is because we wanna make a new array into it, because or else it's gonna keep changing. All right, because you don't wanna pass by reference, because or else it's gonna keep changing. All right, now for I in range, so what we're gonna do is, depending on where we start, we're gonna start at 0 index anyways, but depending on where you start, you want to iterate on all of these numbers, okay? And this iteration is actually this spot. You're doing, like, go back to the thing, you're doing this spot right here. You're choosing for this guy, which spot do I want to swap with? I want to swap it for this, and then for this, and then for this one, which is the same as iterating through this first pass. And then for each iteration, you're gonna recursively call that function, and this function will deal all of this for you. It's gonna do all of this for you. All you have to do is tell it the beginning, which what you should do in the beginning, right? So that's recursion will help you do all of this. You just have to specify this. Okay, cool. So for I in range that, so what do we want to do? We want to swap with all these different these guys. So you want the start number, and then what you want to do is you want to swap with whatever the iteration goes to. So you're going to swap with every single number in this array. So we're going to swap like this. All right, and then what do we do next? We're going to permute the whole thing. So we're going to recurse, and start is going to be +1 because you want to call permute helper on everything else that's not yourself, because currently you're at that index, you want to permute everything, so you can assume that this already works, that everything is already good, that magically it works. All right, that's how recursions work. And then what you want to do here, you want to make sure that you swap back. Why is it important to swap back? That's basically what backtracking is. You don't want to mess up the array so that when you send it to like the next one, it's gonna be an array that has been into a state that you don't want to be in. So you're gonna re-swap them back, so now it's back to normal, right? Because you want to swap the first number for like, okay, let's look at here. Let's back in the iPad. You want to swap this number with 2, but then if you don't swap back, then you're going to be swapping the 2 with 1 or 3 again, which is not good. That's why you always have to swap back. So you have 1, 2, 3, and then you swap to, for example, 2, 1, 3, but then you want to go back to 1, 2, 3 so that you could swap with another guy to swap for like 3, 2, 1, for example, right? All right, cool. Now back to the code. Okay, so now that we have this recursion done, this function is done, what you want to do is you just want to call it. So permute helper, and then start is 0, and then the end is the length of nums. Cool. Actually, we might not even need the end. You could just have here, you could just have length of nums. So technically, we don't even need this. Length of nums. -1. Okay. Do I use it anywhere else? Okay, delete this. And then length of nums. You don't need this anymore. Okay, permute. All right, and then we just return the result that we used. And then let's run that, see if it works. All right, perfect. The test case works, and yeah, this works perfectly. So yeah, that's pretty much how you do this question, permutations, and that's the basis of backtracking, which will be very, very useful to solving a lot of these different problems. The only thing that's different is you have to be a little bit more creative in terms of understanding that it is a backtracking problem, and then sometimes you have to filter certain like tree structures. Like for example, back to this tree, sometimes in backtracking problems, to make it a little bit more efficient, you could stop like here, for example. You could not compute certain areas because you have rules. For example, like chess, there are certain moves that you just aren't allowed to do. So you could remove the whole subtree, so then your backtracking will be more efficient. All right, cool. So that's pretty much it. Thank you for watching, and see you at the next one.